One 6 meters tall. And one 15 meters tall. Alex, what's a meter?
A unit of length.
Yeah, who the hell knows? We're American. We don't use meters, right? What the hell?
We're like one of 5 countries that uses this stupid customary system.
I think it's called the imperial system. What a great name for it, right?
Yeah.
Two poles, one 6 meters tall and one 15 meters tall, are 20 meters apart. Is that it? US, Liberia, and Thailand? Well, Liberia was founded by former American slaves, so that kind of makes sense since they came from America. Thailand, I don't know why. I wonder what the historical reason for Thailand using it is. A length of wire is attached to the top of each pole. And it is also staked to the ground somewhere between. Where should the wire be staked? So the least amount of wire is used. You miss measuring things in meters. Come on. So let's see. So there's the 6. Come on, Notability. Stop trolling me. There's the 15. And there's the 20. And so somewhere in between, you stake the wire, say over there. So that's what this looks like. We have 2 poles, and you want to put a wire between them for some reason. So I asked this to the other lecture because they had an optimization problem that was also a little tricky, and it wasn't exactly clear at first how you go about solving it. And a lot of students said they felt intimidated by this. Do you guys feel intimidated by optimization problems? Are they scary sometimes? Yeah, probably, because they're word problems, and they all feel a little bit different, right? Even though they're kind of the same, they still feel a little bit different. So I want to convince you that you do know how to solve these problems, right? So what do we do in general for these problems? Let's kind of make a little roadmap for optimization problems. Let's remind ourselves of what to do. What are the sorts of things we have to do?
We have to make a constraint equation.
So constraints. Okay, so we have to find the constraint equation. So identify constraint. Okay, that's going to be one of the things. What else do we need to do in these problems? I'm going to write constraints with an S because sometimes there are more than one. We know that. What else do we have to do? Nothing? Peter, you know what to do. What else do you have to identify? You have to identify the constraint? No, you're not sure? Emily just saved you. Objective. Identify the objective. Okay. What's after that? I mean, why do you use the constraint? What's the role of the constraint equation? Think about that and then answer the question, what is the next step here? What is the role of the constraint equation? Get to one variable, right? The constraint equation, its role is to be able to solve for one variable in terms of another. So I'm going to write here, write objective in one variable. But you know to do that, you use the constraint equation. Okay, what else do we need in an optimization problem? Do we remember? You don't have to get this to me in order. You can kind of just say what you know to do at some point. We'll put it in order. Find the absolute min or max. Guys, that's your ultimate goal. Dina, how are you actually going to find the absolute min or max? Like, what are the steps to finding a min or max? Critical points, good. So we're going to get critical points. Oh, and interval of interest, right? Emily has that, interval of interest. And then Dina says you define the absolute min and max, and Kai clarified that means we define the critical points. I have to actually put down what is my answer, right? Write the final answer, because sometimes they want the dimensions of the box. Sometimes they want the actual volume, right? It just depends. And there's something in between here that's very, very important. Sign chart, right? So you don't necessarily have to do a sign chart, but the sign chart is part of justifying or verifying the min or max exists. Okay. And like I said, this is the calculus portion, and this is the non-calculus portion. So I'm going to leave that up there for a second. So now let's go back to our problem. So let's start thinking about what is the objective. What is the objective for this problem? Even if you don't have variables quite just yet, can you at least describe to me in English what the objective will be? Right, baby steps. And how do you know, how do you identify the objective from this question? Like, what are you looking for? Minimum amount of wire. I think I actually said least amount of wire. Yeah, least, but whatever. Right, how do you know what you're looking for with the objective? You look for those, what are these words called? This is now an English question. I taught this to you last time. What are those words called? No one remembers. All of you don't know. Should I get your XPOS teachers here? They would be very disappointed in you. Your high school grammar teachers, they're called superlatives. Right? You're looking for that word least. So whatever follows the word least tells you. So the amount of wire. So I'm looking for a length. So the objective is going to be the length of the wire has to be minimized. Our objective is the total length of wire. Now that comes in two pieces, right? So I'm going to call these things, I'm going to call this L1 and I'm going to call this L2, the two pieces of wire. So my objective function, let's call it F. It's a function of L1 and a function of L2. And the total length is what? L1 plus L2. That is my objective function, L1 plus L2. Now, what is the constraint?
Is it just L1 plus L2 is equal to, no, wait, we have to equate this to 20 because that's the total length.
Well, that's the total horizontal length. 20 is the total horizontal length, right? The objective is the length of the wires, which will be different depending on where you stake this. If I stake it, very close here, it's going to look like this. And that is a different total length. However, Jitesh is right that the horizontal length has to be 20. So let's actually make a note of that. So our constraint is that the total horizontal length is 20. But the question is, how do I incorporate that into the problem? So Pythagorean theorem is going to come into play here for sure. So I think we actually need to introduce another variable. I'm going to introduce, well, actually, these are not similar triangles, Karen, because they don't share an angle. These angles are not necessarily the same. So they're not similar triangles. So I'm going to call this length here X. Actually. I'm going to call this horizontal length x. And our constraint, the fact, right, Jan says the distance from the left pole to the stake is x. And the fact that the total length is 20, that means actually our constraint is very subtle. Our constraint is that this length is 20 minus x. That's actually where the constraint is being used. Now, what is the next step of the problem? Well, we need to somehow write this in terms of one variable. So the easiest thing to do in this case, I can write L1 and L2 each in terms of this third variable x. And that's what we're going to do. So this problem is a little bit trickier and a little bit different from the other problems we've been working with, because if you look back at the other problems we've been working with, usually what happens is the variables that are in our objective, one of them is in terms of the other. Like if I had x plus y, my constraint might be like x times y equals 10. But actually this is a bit different because my objective is in terms of L1 and L2, but I actually want them both in terms of this third variable that up until now I have not introduced, or I have at this point x. Right? That's what makes it a little bit different from the previous problems we've been working with. But that's okay, right? The ultimate goal really is just you need an objective in one variable. It doesn't matter what that variable is, just in terms of one variable. And we're going to use the variable x. I will also say the variable x is not like being just picked out of our asses, right? I mean, we're not just doing it randomly. I mean, the question did ask, where do you put the stake, right? I mean, how would you tell a person where to put the stake? I mean, you're not going to tell them, oh, put the stakes that this length is 20 and this length is 10. No, you're going to tell them, put the stake 5 meters away from the left pole, right? You're going to give them a distance between the two poles of where to put the stake. So it's natural to introduce this variable x. Okay, so in terms of x, very simple geometry shows us that L1 is the square root of x squared plus 36, and L2 is the square root of 20 minus x squared plus 15 squared, which is 225. That's very simple geometry, right? Pythagorean theorem. Oops. So that means, so our objective is so now let's call this f of x. So remember, it was L1 plus L2, right? That was our objective. Did I get out of L1 plus L2. That's my objective, one variable. Now let's get the interval of interest. So what is our goal? Our goal is find the value of x that gives absolute minimum of our function f of x. I'm not going to recopy it. On what interval? What is the interval of interest for this problem? What are the allowed values of x? 0 to 20. 0 to infinity? It's actually 0 to 20. Right? The stake has to be in between. Now, Chi included both endpoints. Is he right? Am I allowed to stake this at 0 or 20? Yeah, why not? I can just put the stake right here, and then I have a wire going down and a wire going like that, right? Or I stake it at 20, and I have a wire going down here, and then a wire like that. There's no reason why I can't stake it on the pole. So 0 to 20, including the two endpoints. Now, can someone remind us, why does a closed bounded interval, you should look at a closed and bounded interval. If you have a closed and bounded interval, you should get excited. Why is that actually a good thing to be able to include both endpoints? Emily says guaranteed min or max. I don't know why that's in caps. Well, because you're very excited, Emily. Right? I need to make up for the Penn State shirt. So we're very we're very excited, right? Because if you have a closed and bounded interval, if the function's continuous, that means the min and max are guaranteed. So that whole nonsense about, I mean, it's not nonsense, but that whole business about doing a sign chart or doing the concavity, you don't have to do it. You just need to check the critical point and the two endpoints. The min and max is guaranteed, right? You don't need to do any justification afterwards. So that's nice. Okay, so now let's actually find our min and max. So critical points. And let's be very careful here, because the algebra is going to be, if you're too zealous, the algebra is pretty much impossible. So the function at the top of the screen. So my derivative is, so I get 1/2 the thing to the negative 1/2. So that'll put the square root in the denominator. And then I get times 2x by chain rule. So the 2's will cancel out, and you actually get this for the derivative of the first term. Right? So you have a 2 and a 2. You actually have 2x from chain rule and the 2 and the 1/2 from the power rule, but they cancel out. You can check that yourself. And now we have plus. Now we have a square root in the denominator. Right? 1/2 that thing. But then we get 20 minus x times -1 by chain rule. The 2's cancel out, and I can put the negative on front. So if you work out that derivative, you'll see that you can actually write it like this, put a minus there instead of a plus, and a 20 minus x there. Okay, so again, I trust that you can do the derivative yourself, and it simplifies to this thing. Notice I am actually I'm not squaring this out. I'm actually keeping it as 20 minus x squared, because I think for now, that's actually a simpler presentation of the function. Maybe later I'll expand it out, but right now I kind of want to keep things simpled and factored. And now I need to set this equal to 0. Now, when you set this equal to 0, do some of you get nervous because you don't know how to solve this? It looks complicated, doesn't it? A little bit. So let me actually go through the algebra with you. Okay, so I move everything over to one side. So this is a minus, I move it over to the other side. So I get x over square root x squared plus 36. Then, to get rid of the square roots, I square both sides. And again, notice that the top, I'm just writing as 20 minus x squared. I'm not multiplying it out, but I've squared both sides. Now I cross multiply. So when I multiply these two things, here, the better thing to do, I'll highlight it. So when I do cross multiplication, here's one cross multiplication, and then here's going to be the other one. So what I've written down so far is the green thing. And if I cross the other stuff, I get x squared 20 minus x squared plus 36, 20 minus x squared. And that's the blue stuff. I'm going to center it as well. So hopefully you can follow that algebra, right? So I've cross multiplied. Why don't you need another parentheses on the left side? Well, what I'm doing is I'm taking the x squared and I'm actually distributing it to each term. And the same thing when I do the blue stuff, right? I'm taking the x squared, multiplying, and the 36 multiplying. I'm actually expanding it as well, but I am keeping terms grouped. Like I am keeping the 20 minus x squared together. I'm not expanding that squared just yet. Yeah, cross multiplication. It's like cross multiplication is like the magic of algebra, right? Now, what do you notice? Nice. These things cancel out on both sides. X squared, 20 minus x squared. They actually cancel out. So imagine if you had actually expanded everything out from the beginning, you'd have had a whole bunch of crap on both sides that you would have actually had to cancel out individually. And that's if you actually did all the algebra correct. But now we see that they cancel out entirely. And we actually now get something very nice. Sweet. And now you can take a square root. So if I take a square root, what do I get? I get 15x equals 6 times 20 minus x, or 15x equals negative 6, 20 minus x, right? So I take a square root and I get plus or minus, right? And now you can solve this. This is very easy. 15x equals 120 minus 6x. So I get that x equals 120 over 21, or 40 over 7. And for this one over here, I get 15x equals negative 120 plus 6x. So I get that x equals negative 120 over 9, which is no good. First of all, it's not in the interval. Second of all, it's not. It doesn't even solve the equation. If you go back to see this, it actually doesn't even solve the equation. But I'm going to say not in the interval. So our only critical point is 40 over 7. Now, isn't that algebra a lot nicer if you remember, if you thought not to expand things out? Right? Don't make things uglier than they have to be. Keep things nice and simple. In any event, any questions about any of that algebra or how I got to that critical point, 40 over 7? Alrighty. Now, we've already discussed this. I have a closed and bounded interval. So do I need to verify that the min and max exists? No. I check the value at the endpoints and I check my value at the critical point, and that's it. Okay. Since 0, 20 is closed and bounded, we know the min and max exist. So we check a table of values. So what was our original function? It was this thing. It was this kind of ugly looking function. So here's my x value. Here's my y value. I can make this a little bit smaller. So my x value, I need to check 0 and 20. Those are the endpoints. And then I need to check 40 over 7. So 0, you can check, just gives me whatever the hell it is. I have it all here. 0 will give me 31. You get 6 plus 25. You get 31. If you plug in 20, you get square root 436 plus 15. And that's approximately, get out a calculator, that's approximately 35.8806. And then if you plug in 40 over 7, miraculously, these are actually both perfect squares. You get 58 over 7 plus 145 over 7. Together, that makes 29. It's amazing that that actually gives you an integer answer, isn't it? And so we can see that the minimum is 29. So the min is 29. We should put the stake (40 over 7 meters to the right of the 6-meter pole.